A hearing aid equipped with a vacuum tube was developed as an amplifier in the 1920s, but it was too large and expensive to be put into practical use. When the transistor was introduced into the hearing aid in the 1950s, the size of the hearing aid became smaller and could be reduced to the size of a cigarette pack, and an earring-type transistor hearing aid was also developed. Recently, digital hearing aids that digitally process signals have been commercialized, and the characteristics of the amplifier can be controlled by connecting a hearing aid and the computer. The hearing aid consists of an input device microphone, a type of converter that converts an acoustic signal into an electrical signal, an amplifier that amplifies the converted electrical signal, a regulator that controls the characteristics of the amplifier, a power source that supplies electrical energy to the amplifier, and an output device receiver that converts the amplified electrical signal back into an acoustic signal. The amplifier is the most important part of the hearing aid, and in order to actually complete the electric circuit of the amplifier, several electrical devices such as transistors and diodes and capacitors are required. Its characteristics vary depending on how the electric circuit of the amplifier is configured using this. From the following, we will explain fast Fourier transform, FFT, which is the basic algorithm for digitally processing signals in hearing aids. To understand this, we first need to know the definition of Fourier transform. Fourier transform refers to a transformation that breaks down a function of time or space into time or space frequency components. Joseph Fourier used this transformation for the first time in his research on thermal conduction to find the solution to the thermal equation. In the complex function obtained by Fourier transforming a function of time, the amplitude at each frequency represents the size of the frequency component that originally constituted the function, and the deflection represents the phase difference from the basic sine curve. Fourier transform is a transformation method that can analyze the frequency and express the size of a wave contained in a signal. When a signal is detected, Fourier transform can create the various applications by transforming it into frequency units and expressing its amplitude. Simply proceeding with Fourier transform requires a huge amount of computation. If there are 2,048 analysis targets, 1,048,576 real numbers and complex number multiplication operations are required. FFT is a unique algorithm to eliminate excessive computing power consumption during Fourier transform. By improving the n-square operation to n-log n operations, it laid the foundation for a truly dramatic speed improvement. It is used in many fields, from digital signal processing to algorithms for finding the root of partial differential equations. The algorithm used for this FFT is the Cooley-Took algorithm. To explain the Cooley-Took algorithm, it is first necessary to understand the concept of division, the definition of DFT, and the concept of the Danielson-Wrench's lemma. A division is to divide a sequence of length n into two sequences by collecting only those whose index is even and those whose index is odd. Discrete Fourier transform is the transformation between a discrete time signal and the discrete frequency signal. The actual signal is finite and consists of individual data points. This is because seismograph signals may appear continuously, but they cannot be recorded with infinite precision. Due to the limitations of data measurements, they are bound to be discrete and finite. Thus, an ideal Fourier transform is not possible. Instead, we use discrete Fourier transform, DFT.
First, the question is why are we using the discrete Fourier transform? DFT transforms the signal from the time domain or spatial domain such as distance to the frequency domain. One of the main reasons for making this transformation is because the features of the signal that we are interested in are not always clear in the time or spatial domain. For example, here we have two time domain signals sampled at 200 Hz, and the question is which of them has a significant 60 Hz component. These aren't that obvious and they both look pretty similar. But if we transform them into the frequency domain, it's much easier to answer. That means this is clearly the first signal because there is this big 60 Hz peak. So we can use the frequency domain to understand the frequency composition of the signal and how the DFT performs these transformations. I made a little MATLAB application here to show you how the DFT works. Here, the time signal x sub n is just a pure sine wave with 10 samples. So per the definition of the DFT, we multiply this signal with e raised to an imaginary exponent, which I'm calling this whole thing the correlating signal, and hopefully the name will make sense shortly. Now, if we send k equals 0, then our correlation signal is just e to the 0, which produces a constant real value of 1 and imaginary value of 0. And when you multiply this our time signal and then sum the result, we get a value that is really low, and mathematically, this is because when you multiply the time signal by 1, we get the exact same signal back, and so essentially we're really just summing the values in our time signal. And there are equal positive values, that's these 4 right here, as there are negative values which are these 4, and so we cancel each other out to near 0. And the way that we can think about this really low value is that our time domain signal is not correlated very well with a signal with 0 frequency. Now let's move on a new set of frequencies, say k equals 1. Our correlating signal now consists of sine and cosine wave with a period equal to the length of the time signal. And if we multiply this with x sub n and then sum, the result of the value is larger. And we can visually see that the correlating signal is near the same frequency as our time signal. And so, at least for the imaginary component, which is perfectly out of the phase with our time signals, the product of the two is always negative. And therefore, the summation is also going to be negative. So, there's a strong correlation between the two at k equals 1. And if we move to k equals 2, the correlation drops again. And this is all the DFT is doing. It's going through in different frequencies where k goes from 0 to n-1 and calculates the correlation between it and time signal. Daniels-Lanchos lemma can be derived like this. Kulichuk algorithm is a divide and conquer based algorithm. Divide and conquer is a representative type of algorithm that makes n-square operation into n-log n operation. In computer science, divide and conquer is an algorithm design paradigm. A divide and conquer algorithm recursively breaks down a problem into two or more sub-problems of the same or related type until these become simple enough to be solved directly. The solutions to the sub-problems are then combined to give a solution to the original problem. In the case of DFT, its term from k equals 0 to n-1 requires n multiplication, resulting in a total of n squared 2 multiplication overall. However, a DFT of length 2 half n can be computed with n squared 2 quarters multiplications, having the computational workload due to this partitioning. Moreover, rather than immediately computing upon partitioning, the data is continuously split until there are only 2 data points remaining. This recursive splitting process continues until the computation reaches the final stage for the 2 remaining data points. Then the result of these 2 data points are combined upwards while merging, effectively performing the computation for the origin and data points. Consequently, with this approach, the division process occurs log n times, and after its split, merging requires constant time calculation for n data points. Thus, with n log n computations per layer, the final result can be computed. Thank you for listening.